Okay, welcome to another training video from the Yale School of Medicine X-ray crystallography core laboratory. In this series of segments, we'll be looking at our X-ray generator and our fairly new detector, which is a Pilatus 200K bidextrous. The entire system has been put together by Rigaku. So what's nice about the Pilatus is that it's a pixel array detector, so it allows you to do shutterless detection, and it is direct measurement of photons that hit the detector as opposed to a CCD camera or an image plate where it's a secondary measurement system. The system also comes with a 4-axis goniometer, the AFC11, that allows you to move the detector to theta. Also allows you to move phi independent of omega, which is the rotation axis of collection. It also has a chi axis rotation ability. The 4 axes of rotation allow us to maximize data collection time and efficiency. So, other values of this detector: one, it's in-house with nice crystals. There's no need to go all the way to a synchrotron or a different source. We've routinely collected excellent data on the Pilatus, and we've even collected several data sets better than 1 angstrom resolution, which is more than enough. Also, if you are planning a trip to the synchrotron, as far as I'm concerned, it's essential to pre-screen your crystals, get the cryo right, make sure that they are single crystals, get everything frozen and ready to go here before you either ship your container for remote access or travel there, that way you know what you're working with before you get there. In the meantime, you can collect the data set here to work with. So, like all the instruments in the X-ray core facility, door access is restricted through ID card activation. Contact me for that. And schedulebook.com has our scheduling system. The Pilatus is scheduled by the hour. You can schedule up to three days in a row if you feel you need that. You can get longer times if you want to collect or screen many crystals over time if it's not busy with other users. Okay, for using the X-ray detector and generator system, of course, safety first. So I'll go over some of the safety requirements. First of all, you have to be officially trained and authorized to use the system before you do. That consists of 2 parts. There's an online training system at the EHS website. It's called XRD Training Part 1. You'll take a quiz, pass it, you'll be fine. Then there's XRD Training Part 2, which you'll have to do hands-on. I'll show you the machine, the safety protocols, etc. I'll sign that, and then you'll be able to get it. Also, you're going to contact Radiation Safety and get yourself a dosimetry badge, as well as a dosimetry ring that you need to wear. So the entire time you're working here, you should be wearing your badge and ring badge. When you're not using it, store it in these metal drawers here on the top shelf, or top drawer, and that way it'll be here. And every 3 months I recycle them with EHS, and they measure them. They've always come up negative or at 0, so you don't have to worry about that. If you use the badge in your own lab for isotopes or something like that, and you're a lab manager or whoever recycles them that way, just continue to do that, but bring your badge down here when you need it. Also, of course, you want to have your basic PPE on, gloves, lab coat, safety glasses. This is especially true if you're using liquid nitrogen. So the liquid nitrogen is in the hallway. In the drawer over by the HPLC, by the door out to the liquid nitrogen, there's a pair of gloves and an extra pair of safety glasses. Please use those, especially since you're in the hallway. Also, there should be a box of nylon gloves in one of these drawers that you can use. Those are very useful for when you have to handle liquid nitrogen so you don't get frostbite in your fingers. Alternatively to that, you can put on 2 or 3 layers of nitrile gloves. That's what I usually do. So once you have door access, you're able, and you can sign up, you can use it whenever you want. If you have guests, which would be other researchers in your group, maybe a new graduate student or a rotation student, and you want to show them the system or even help them collect data on some of their crystals, that's fine. You just have to, unauthorized users can't use the system even if you show them how to do it, and they really shouldn't even be kind of around it while it's running. That being said, you can bring them, just you're in charge of them for that time. Okay, so there's a variety of tools that are provided to use with the X-ray generator. I'll just go through them. There's liquid nitrogen tanks in the hallway. There should be, there's two, usually one's partly full and one's full. If they're empty, let me know right away. In addition to that, there is a dewar that belongs here. You can use that. If you need to borrow it for some reason, bring it right back. Again, there's a set of gloves and safety glasses for the liquid nitrogen. There is this type of dewar that holds this device that allows you to put vials in it to freeze the crystals. The height adjustment tool is here. There's another dewar here that is sort of a taller cylinder for pre-chilling the crystal manipulation tools. The dog dish for liquid nitrogen, for bringing your crystals in and out of the vials. There's a little plastic tub that has a whole bunch of assorted forceps, clamps, the crystal wand tool to bring a pin to and from the goniometer, and a couple of different types of magnetic wands that you can use. Most of these are labeled. Please don't borrow them, bring them to your own lab unless it's necessary, and then bring them back. We're going to store them all in this bucket here. And when you're done, all the dewars should be warmed up to room temperature, dry it out, and then store all the tools in these drawers right below it. Other things you might need are some loops. Now, I have a few loops here. You're pretty much required to bring your own loops. I can't, they're all different sizes and styles. You have the classic Hampton ones. A lot of people prefer the mitogen ones. Those are nice. Those you should bring. I do have some if we need them in an emergency. Again, your radiation safety badge, you should have that with you. Your safety glasses, and then we have some nylon gloves. So this is the microscope that we use. The range of the magnification here is just listed as 1 through 7. At position 5, that allows you to easily determine the size of the crystal. So one of the major units at 5 is 200 microns. If you, for some reason, need to move the microscope around, do not pick it up by this black stage. That's not permanently attached. There's really no reason for you to move it anyway. And we have a shipping dewar for the liquid nitrogen dewar. This serves as both the storage in this lab, as well as you can borrow it to mail to the synchrotron or not, and back. For the most part, it stays here. If you want to use it to mail it, let me know. The only rule on that is I test it periodically, so if you're going to mail it, if they kill it in the mail and it doesn't hold vacuum anymore, you're responsible for it. Okay, in this next section, I'd like to talk about the basic anatomy of the generator and the detector system. So, the X-ray generator itself, the real working component of that is within here, which is known as the tube tower. So we have a rotating copper anode and a filament made of tungsten in there, and that's where the X-rays are produced. So that solid copper box is under vacuum, and when we apply current to it, the X-rays get generated from the copper anode. So as far as safety is concerned, the X-rays are contained within the copper tube tower and only allowed out when we open the shutter. If we look down below, this is the control unit for the generator itself. It's all the electronics. Under normal circumstances, when you should see it, it should say X-ray on now and 40 kV, 20 milliamps. That is one indication that it's ready to go. Another thing is that this red light here, that indicates that the X-rays are being generated within the tube tower. If that's not lit, there's a major problem. Let me know. I'll see if I can fix it. Okay, following the tube tower, on the side of the tube tower is a beryllium window. So beryllium, that particular element, it's metal, so it can be bolted in place and hold a vacuum, but it's also X-ray transparent, so that is what allows our X-ray beam to come out. On the other side of that is a copper shutter that is computer controlled that can open to allow the beam out. The beam will come down the mirrors here, and that will focus it into a fine beam as well as clean up the wavelength. So we have very monochromatic light. Continues to come down the collimator. Comes out the thin part of the collimator, and there is a 0.3 millimeter width pinhole at the tip where we get to where the sample is held by the pin. Other things to note here are the cryo stream is here. So that's 100K gaseous nitrogen that comes out. From in behind the machine is a nitrogen generator as well as a compressor that runs that, as well as a control wire. That should be pointed directly at your sample. Here's your beam stop. That should be in place when you're using the system to block direct beam from hitting the detector. The goniometer is here. So the phi axis will rotate this way. This is our chi arm, where in particular data collection, we can rotate chi up like this. The crystal will stay centered, but we'll be able to get a better collection of all our HKL indices. This is the detector itself. It's on a 2 theta table, so the detector can swing out and allow us to collect higher resolution data. One thing to keep in mind is that the front of the detector here is actually the detector itself. It's not a glass coating or anything on there. That being said, it's very fragile. So when you're working in here, be extremely careful around the detector. If you don't trust yourself, you can use the computer itself to manually move the detector farther back. So I think it's at 200 millimeters now. I think you can go back to about 400 millimeters if you want it out of your way. Just be extremely careful of that. You can cause a lot of damage really quickly. Okay, so that's the basic anatomy. The only things that should be in the hutch area here behind the doors are the 2 tools used to center your sample on the goniometer, which I'll get to in a later segment. You'll have those. And pretty much the only thing you should be touching is the tools, the goniometer itself, and maybe this fiber optic light to light up your sample. And you can see in the back there is your video display that has the crosshairs of where the beam is, and that's where you want to line your crystal up. Please don't put anything else in here, especially buckets of liquid nitrogen. If you manage to spill the liquid nitrogen, it's going to get on all the control computers that are down below. We're going to have condensation. It's going to be a mess. So there's no need for that liquid nitrogen in here. Okay, so the way the safety mechanism works on these doors, which is really nice, is that there's 3 leaded glass doors, labeled 1, 2, 3, and the aluminum housing is also labeled. So you'll slide them over in place, 1, 2, 3, and the center one, number 2, will fit exactly. It'll click right in place. Once it's there, You can push this green button here, and it should light up. At that point, the computer or the generator and the computer control knows that the door is shut and it's safe to open the shutter when we ask it to. This prevents accidental exposure to the direct beam, whereas let's say I've left something in there that I forgot, or I wanted to readjust the crystal and I open the door, the light goes off immediately. So if the shutter was open, it would shut the shutter. So to avoid confusion in the lights, the large red light here is the X-ray on light. That simply means the X-rays are being generated. This small red light here, that only comes on when the shutter's open and the experiment's going. So you should only see that light on when the doors are shut, this green light is on, and you told it to open the shutter. Okay, so the control computer is over here. The computers themselves are actually under the machine. There's just the video cables and stuff come over here. You want to start the software here. It's this icon that says HKL3000R P200SK Chi. Double click on that guy. And the HKL3000 interface should come up. It's very similar to HKL2000, which a lot of people are used to, except now it has this Collect tab. So if you click on the Collect tab and hit Connect, this little terminal window should come up and it will initialize the detector. So if we look at the goniometer setup right now, we can watch the goniometer itself initialize. So right now it's calibrating the distance. And it goes through and it calibrates and checks the motors for the different parts of the goniometer. And you should only have to do this once when you start the software and connect. In between crystals, it's just a matter of changing the crystal name, that kind of thing. Okay, so once the goniometer is done initializing, it should be static. You want to wait till it's static before you try to load up a crystal because you don't want to accidentally bang into it. And at that point, the terminal window should end with off result equals success. If it says anything else, like an error or whatever, call me up or find me and I'll see what's wrong. So that's the basic layout of the machine. In a subsequent step, we'll go through the software and see how we collect the full data set. Okay, in this segment, we're going to talk about getting your crystal mounted onto the goniometer on the machine before you collect your initial images and evaluate the crystal. So whether you're using a 24-well tray that you set up, or a variety of a 96-well tray, sitting drop, hanging drop, either way, the procedure is pretty much the same. So there's a couple different ways to do it. I'm not going to go into excruciating detail because everyone's got their own sort of finesse on doing this. The simplest way is to set up a little stage to work on, and basically loop your crystal, either with or without soaking it in some cryo solution, and bring the pin and crystal directly to the goniometer and get it into the cryo stream right away. In that case, what you'll do, you take your tray, identify a well with a good crystal, identify which crystal you're going to go for first, and then select the proper loop. So I like to pick a loop size that's just about the same size as the crystal, maybe even a little smaller, so that way when you pick it up, it's holding it rather than the crystal going through the loop. That being said, also if you use the mitogen style loops, they're sort of made to do that. They have that little holding part. Basically at that point, if you, through the microscope, you loop your crystal out. So if we follow over to the goniometer, basically you can, it shouldn't dry out that quickly, especially if you have good cryo. And basically just mount it up on to the goniometer like this. Now what I suggest doing is, before you even loop the crystal, take your empty loop, load it up onto the goniometer, and at least get the height right and get the centering close. You want to do this because even though the pins are all from the same manufacturer size, like 18 millimeters or so, the loop itself might be longer or shorter or bent to one side and whatnot. So you want to get it pretty close so that when you do come in with your crystal, it's into the cold stream right away, and then that way it's safe, and then you can go back and sort of put your well away, and you'll be fine there. Okay, so once you have the height right and you're confident of your crystal, you then go in, cut open the well or remove the cover slip, load your crystal, put that back on the pin and center it. And we'll get to centering in a later segment. Another way that a lot of people like to do it is to, rather than bringing the crystal on the pin directly into the cold stream, do a quick flash freeze into liquid nitrogen and then transfer it up there. There's really no advantage of either way. Depending on your crystal and your condition, one way may work better than others. By putting it directly into the stream, it's a slower freeze, but by plunging it in liquid nitrogen, it's a much faster freeze. In that case, what you would do is you would have your crystal manipulation tools pre-chilled. So my the tongs to hold the pin, I have those pre-chilled, and I have my magnetic wand here. So again, I cut open the well, pick the crystal up, put it on the magnetic wand. We have a little dog dish full of liquid nitrogen here. Plunge that in till it stops boiling. Take this tool, and now you have your pin with your crystal within this tool. And then you can bring this up to the goniometer and mount it on there. You have about a minute or two while it's in here that it's still protected from the warm air environment. So there's no need to rush over there and jump at it, because if you go, if you rush, you run the risk of banging into the cold stream or the collimator or something like that. And you can just place that on top of the goniometer. In a minute, I'll show you how to orientate the goniometer so it's much easier to mount a crystal. So those are the two ways to get a fresh crystal out of the tray. Either looping it and putting it directly, or flash freezing it and then transferring it. The third way to put a crystal up there would be one that is already frozen in your doer. So you might have frozen a bunch of crystals up in your lab, or rather than shooting them one at a time, you froze a bunch here. And you have them stored in here, and they'd be stored in our magnetic vials with our pin like so. So if you have these, it's quite convenient to be able to load the crystal up onto the goniometer. So what you do then, you want to do this before you even get into the liquid nitrogen door, is in the software, under the Collect tab, you'll see another sub-tab called the Line here. In this tab, again, it's got another copy of the video feed that is on the small monitor there. But what's most important here is there's this function called Crystal Mount. So that's set up so that when we hit that, the goniometer is going to move around in such a way to make it very easy to mount off of a vial or off of the metal tongs that hold the pin within them. So if we can look at this, I'll click on Crystal Mount. It moves the 2 theta over to about 29 degrees. We're just using that as a backstop from the camera, so you have a little better contrast when you're centering your crystal. It's going to move the chi arm out of the way and move chi up to about 40 degrees. Now if you come in with this tool, there's really nothing in your way, so you don't dislodge any of that, and it's less likely that you'll drop the crystal. Also, when you pull your cane out of the liquid nitrogen, I mean, you can use the tongs. I find it just easy enough just to take the vial like so, and it's mounted. The only drawback to this is you didn't have a chance to pre-align the loop, but you know, if all your loops are about the same size, you're going to be pretty close to the cryo condition. And the machine is aligned such that the crosshairs are correct no matter what position the goniometer is in. That's where the beam and the cryo and everything intersect. So after you've mounted a crystal here, you'll go back to the software and click on the 0 goniostat button, and that's going to put it back to the default position, with the exception of 2 theta, which is actually nice because that leaves the shiny part of the detector over where the camera's pointing and gives you a little bit better contrast when you're trying to center a very small crystal. So those are the 3 ways to mount one, and in the next segment we'll look at centering the crystal and then collecting our initial images. Okay, once you have a crystal mounted onto the goniometer in your sample loop, the next step is to center the crystal both within the beam and the cryo stream and the camera crosshairs. So at this point, as I said, your sample loop will be mounted on the goniometer. Since you already got the height right, it should be pretty close to centered and should be stable in the cryo stream. For this step, you'll really only need 2 tools, which are stored within the hutch here. So you'll need the 5-axis lock and the goniometer tool. So for this Rigaku goniometer, there's also instructions taped over here if you need a quick refresher. So basically the way it's set up is the camera is set up here at about a 40-degree angle offset from the direction of the beam, and the monitor is in the back with the crosshair to let you know where it's centered. So you want to center it in both X and Y direction and then get the height in Z correct. So you can see on the monitor that the crystal is within the loop, and right now it's slightly out of focus, it's off center, and the height's not right. So we're going to fix that, and we'll know it's right when it's centered and it's in focus. So I normally like to get the height right first. So you want to make sure that with this tool, unlock the 5-axis by turning it 1/4 turn. And that should loosen up the 5-axis, and you can rotate it holding this ring. And then the ring that adjusts the height is this thin one here with the ridges on it. So to change the height, hold this ring on the goniometer and rotate this one, like so. And you'll see that in the screen, the height will change. Now, of course, whenever you're working with the goniometer, keep in mind that the nitrogen stream is coming down. You don't want too much exposure on your hands. You can either wear, we have some nylon gloves, which I talked about earlier in safety, or typically I just wear 2 pairs of latex gloves. That seems to be enough. But just watch out for frostbite. So I'm going to get the height right first. And then I'm going to adjust the X and Y. So X and Y are sort of arbitrary. You'll see here on the goniometer itself, there's 1, 2, 3, 4 screw heads. 2 are for X, 2 are for Y. What you want to do is look at where the camera is here and set up one of the screw axes at a 90-degree angle to the camera, like so. And what that'll do is, as you adjust that direction, it should process on the monitor screen in the proper orientation. So what I'm going to do here is adjust the X direction, and you'll see in the monitor screen that crystal will process back and forth, so I want to center right on it. It's still out of focus a little bit, so I'm just going to aim for the middle of the loop. What then I'll do next is rotate the goniometer 90 degrees so that the other axis, called Y, is now 90 degrees to the camera. Adjust that till it's centered. And at this point, we should be able to rotate the goniometer 90 degrees. Fine-tune the centering. 90 degrees again. Fine-tune the centering. And once it's centered, you should be able to rotate it such that the crystal stays in place and doesn't process around. This is a fairly large crystal, so I can, it's relatively easy to center it. The smaller crystal, you want to not look at the loop, just look right at the crystal itself and get it on the crosshair. Once you're comfortable with the height and the X and the Y, you do not need to tighten anything on the upper part of the goniometer. Simply use this tool to lock down the 5-axis, and then the goniometer should be held in position. So once you're satisfied with the crystal centering, and you've tightened the 5-axis, you want to close the safety doors. Here, they're labeled 1, 2, 3, and number 2 sort of fits in its spot, like so. Once they're in the right spot, you'll arm the shutter here and it'll turn green. That'll prevent the shutter from opening if the door's open. So if we were to open the door, it's going to kill the shutter. Then you're ready to go to shoot the crystal to evaluate it. Come over to the computer. If you don't already have the software up, it's this icon here, HKL 3000R, P200SK Chi. That's the one that will collect data. The one that's simply HKL 3000R, you can use the process data without collecting it, or data that you've already collected. So double click on that. The HKL 3000 interface should come up, and what you want to do is hit the Collect tab, find the Connect button here. This small terminal window should come up and initialize for a few minutes. At the end of that, it'll say success down the bottom. If it doesn't, there's some type of problem. Try to find me and I'll figure out why. Okay, once the HKL 3000 software initializes, the terminal at the bottom of the terminal, it should say off, result equals success. That means you're ready to go. If you get any error messages, let me know. I'll see what the problem is. So we have our crystal mounted. The software is open. We're going to take our initial image to screen the crystal and then determine what we're going to do with it. The first thing you want to do, that's the most important, is go down to this base directory here and click in that window and either choose the directory you already have or create a new directory. If you don't do that, all your data is going to be in the root directory, and it's going to be kind of a mess to find things. Okay. So then you'll give it a new project name. So I'm just going to call this one. The rest of this is optional. And then which crystal you're using. Typically, I'll give it a what the plate number was, and then the well number, and then the crystal in that well, sort of keep track of it. And then these descriptions are optional. So the project and crystal name are going to define the file names that it creates. So you want to avoid spaces and special characters because those will be in the file names later. So that's my file name template. Now, when it starts up, the default imaging is to take a single picture with a distance of 60 millimeters for 10 seconds. With 2 theta chi and phi all at 0. That's a pretty good start. So we usually just collect on that, get the one frame, and see how it goes. If you want, if you want to see if your crystal diffracts in a different quality based on how the crystal is held, you can use this 2 frames with step 90 degrees in the omega direction. Click that; it'll then take an initial image at minus 45 omega, and then another one at plus 45 omega. Okay, so we'll collect sets. You can monitor what the goniometer is doing in this terminal window, and you can actually look at it. Up here is the shutter. When that opens up, the small red light that's on top of the generator should also turn on that I talked about earlier. Just confirm that. And then the program D track here. The program D track should open up and display your initial image. So a couple things to note on the initial image here. There's a horizontal bar here. That's simply the space between the 2 detector chips, and the computer knows about that in the detector definition, so don't worry about that. This shadow here is from the beam stop. The crosshairs represent both the center of the detector and the beam position and where your crystal should be. And then these are resolution arcs going out here. Okay, so at this point, you can decide whether you want to keep this crystal and collect more on it with HKL 3000, or if it appears to be salt or disordered or whatever, discard it and move on to your next crystal. In the next segment, we'll talk about maximizing the collection strategy using the 4-axis goniometer. Okay, once you've found a good crystal that you decide you want to collect on, the next segment we're going to talk about maximizing the collection strategy using both the 4-axis goniometer, where we can adjust 2 theta, chi, phi, and omega. Omega is the collection angle where it rotates. And we'll use a strategy program developed by Rigaku that's integrated with the HKL 3000 package. During the initial process here, there's 4 values we want to determine. You want to determine the maximum resolution that your crystal's able to produce, what time in seconds per frame you want to collect at, which is going to also tell you what the maximum resolution is, figure out what your detector distance is optimally, and then what your completeness and redundancy that you expect out of the collection. So the first thing we're going to do is set up a couple of or series of collections where we change the time per frame. That's going to give us our maximum resolution, as well as determine what time is necessary to get to that resolution without having extra time that's not gaining more data. So if we look at our initial image here, we certainly have data out well past 2.29 angstroms. So we're going to determine where that is. And the way we can do that is there is a little ruler up here where if it tells you, based on what the 2 theta position of the detector is, it'll tell you what, in the detector distance, it'll tell you what the edge resolution and the corner resolution that we can possibly collect is. So if I change 2 theta to 30 degrees, the ruler is now going to change. So now at 60 degrees, or 60 millimeters, the edge resolution is going to be 1.43, and the corner is now 1.37. Whereas if we collect in at 50 or 40, it'll be higher resolution. So what I'm going to do is, because I want to get the most out of this crystal, from experience, I know it's going to be around somewhere in this range here. So we can set up a multi-collection, and right now this is a single. And you can list a series of collection strategies. So if we add one, we'll do 1 frame at a distance of 50 with an exposure time of 10 seconds, which is what we just did. Frame width, that's usually set at 0.25 unless you're special circumstances. That's based on the wavelength and the recommendation for the pixel array detector. And I'm going to set 2 theta out at 30. That'll allow us to collect higher resolution data at that distance of 50. Okay? So I'll add another set. It's going to copy all the parameters. I'm going to set the exposure time up to 20 seconds. Add another set. 30 seconds. 60. And 120. Now in this particular experiment, which is a common one to do, is it is a molecular replacement experiment where we have a protein, we've already solved the structure, we soaked in a drug, and I want to see if it's in the active site. So I'm going to come up with 2 data collection strategies. One is to be collected fairly quickly, maybe get about 2 angstrom or so data, so I can collect it and solve it within a few hours, just to see if the ligand's in there. In the meantime, the crystal will still be on the goniometer, and I can come back and collect my high-resolution data set for the next couple hours and get the most out of it. So at that point, I'm going to do some lower exposure times. So we'll do a 1-second exposure, a 0.5, and a 0.1, which is the shortest exposure time. Once you click done, it'll line up your initial collections here. So you'll see it's holding distance constant, the chi and phi are both 0. It holds 2 theta constant at 30, and it has a variety of different times. So what we'll do now is collect sets, and we'll collect through all of these. Before you hit collect sets, just check that the green button on the door is still lit for the shutter. And we'll see in about 10 seconds, we'll see our first result come up here, and we'll see the difference between this image, which was collected at 2 theta equals 0, and 2 theta equals 30 for the same time of 10 seconds. Let's see, our shutter's open. Okay, so here's our 10-second 2 theta at 30 image. So now we can, previously we could only, the detector ended at about 2.2 angstroms. Now we can see the higher resolution rings where we're getting stuff, or data in between 1.8 and 1.6. So this will continue to collect the 22nd to 30 to 60, and then the short exposures. And at the end, we'll go back and evaluate the effect of the different exposure times to determine our maximum resolution and optimal time. So it's completed collecting our initial images. So if we go up to the data tab here, we'll see each one of the initial images listed here. And if we go to summary and add in time per frame and 2 theta, we can review what we collected where we held distance. This is our initial image, where we held distance constant and changed time per frame here. So I'm going to go back to data, go up to our 10-second exposure, and display it using the HKL 2000 viewer. Okay, so now that we've looked at our summary of what we collected, I'm going to use the DTREC program here to inspect each image. So let's open this too. Okay, so this was our 10-second exposure at 2 theta equals 30. Darken that up. And everybody's concerned about maximum resolution. We have some data out to maybe 1.8. Okay, so now we'll look at the 20-second image. And you can see we're doing a little bit better. 30-second image. And we can see some spots almost 1.6. And then our fifth image was 60 seconds. And again, we're out to about 1.6. So I don't think we've really increased anything from 30 seconds to 60 seconds. So far for our high resolution data set, we've determined the maximum resolution at 1.6, although there is some out a little bit past that, so we'll probably collect at 1.5. That way we don't miss anything. Our time per frame will be 30 seconds. That seems to be, after that, is unnecessary. And while we have this open, let's look at our short collections to see what time is appropriate for our low resolution data set. So this was 1 second exposure. And we certainly still have data out to 1.85. So if we want to collect a 2 angstrom data set, 1 second's perfectly fine. Um, 0.5 seconds, again, we can see data out to 1.85, although our signal to noise is gone down significantly in this part of the detector. And finally, .1 seconds per frame here. We have data maybe out to 2 angstroms. You can see the signal to noise isn't very good. So if I were to collect a quick data set just to get a 2 angstrom result for molecular replacement, I'd probably go with 0.5 or 1 second. So we'll do 0.5 today. Okay, so we've identified 2 of our 4 parameters. Maximum resolution, we're going to go with 1.5. Our time per frame, 30 seconds. And for our low resolution data set, we'll do that at 0.5 seconds. And detector distance. So at that point, we're going to go back to the collect tab with the multi setup. We can switch back and forth between single and multi here. Add edit sets. The first one we'll do is the same as we did before. So 2 theta equals 30. Exposure time of 30. And our distance was 50 last time. And what I want to do is figure out what distance that I can put the detector close enough where we get as much information as possible, but where the spots aren't overlapped. So if we add a set, the closest distance you can do is 27 millimeters. 40 is usually a good one. We had 50, 60 is the default, so let's do 65. Yeah. See where how that looks. So depending on your unit cell dimensions, you may want to have a farther distance to avoid spot overlap, especially if you have one of the distances in your unit cell very long. So those are different distances, 30 seconds a frame. So we'll collect those sets. We'll let that run for a few minutes and then evaluate what distance is best. Okay, so we've just finished collecting a few images where we held time per frame constant at 30 seconds, 2 theta constant at 30 degrees, and adjusted the distance 50, 27, 40, and 65 millimeters. So let's take a look at what we got. We'll first look at the image at 50 millimeters. And this is a repeat of what we collected earlier. So what you're looking for when you're trying to optimize the distance, don't be concerned about losing spots off the edge or about empty detector space. What we're looking for is how to get the detector as close as possible without having a lot of spot overlaps. And because overlap spots will be rejected, and even if they're not directly overlapped, your background calculation is going to include spots near it. So this is at 50 millimeters. So if we look in this region here, there's really no overlaps. Spots are separated fairly well. So 50 is good. So let's open 27 millimeters. And again, this is as close as the detector can go. So we can see here, obviously a lot of the detectors not used as this crystal doesn't diffract, very past 1.5 or so at 30 seconds. And if we zoom into the middle, yeah, a lot of spots are overlapped, and the ones that aren't overlapped are right next to each other. You're gonna have you could collect here, but your data is going to look terrible at the end. What you want to avoid is making that mistake of putting the detector up too close and simply doing one sweep where you rotate, 180 degrees. That's a very inefficient way of doing it. So next, let's look at 40 millimeters. Okay, so this isn't too much different than our initial 50 millimeters. Again, you got good spacing between the spots. That should work. And finally, we did one out at 65 millimeters. Now you can see there's plenty of space in between the spots. So if we had a unit cell that was, one of the dimensions was twice the size, there'd be another spot right in the middle here. So this may work for that. We might even have to go a little bit farther out in the detector. But for this crystal, either 65, 40, or 50 is acceptable. So I think I'm going to use 40 millimeters for my initial lower resolution data set, just to get a quick data set to do molecular replacement on. And that's going to be where we do a ½ second exposure. And then for the high resolution data set, we'll do 50 millimeters. So our 4 parameters that we're trying to come up with were maximum resolution, which is 1.5, time per frame, 30 seconds, detector distance, 50 millimeters, and then completeness and redundancy. Usually you want completeness to be 99, redundancy a minimum of 3, and more than that if that's what you want. So next what I'm going to do is index one of the initial frames. Doesn't really matter which frame you index. You want to use one that's more representative of what you're actually going to collect at. So we decided 30 seconds, 50 millimeters, and the 2 theta is going to get adjusted by the Rigaku strategy program. So I'll index this, and then we'll go into the Rigaku strategy program. Okay, after your initial images are collected and you've decided on your maximum resolution, time per frame, and detector distance, you would have wanted to index one of the frames. So I indexed the first frame I shot at 2 theta equals 0. I know this crystal is going to be P212121, and it's indexed and ready to go. So in order to use the Rigaku strategy program, you want to index your frame as well as you can, and then integrate a single frame. So to make matters simple, I usually delete all the pending sets except the one I'm working with, index that one, go into integrate, and simply integrate that one frame. So that's going to give us one .x file that we're going to use in the strategy calculation. So if we go up to the strategy tab here, we have the original HKL 2000 strategy window that you can use. We also have this additional button here labeled Rigaku strategy. That's going to open a separate program over here, which is the collection strategy. It's going to give you a warning here at the beginning, so you want to make changes. The beauty of this strategy program is it really maximizes the ability of the 4-axis goniometer to get the most out of the pixel array detector and reduce the collection time. So if you integrated a frame in the last step, it has that automatically loaded here. It renamed it into the strategy folder, and it should have your data here. From that indexing. So at this point, we're going to put in fill out the parameters of what we want it to do. So for completeness, you want to leave that at 99%. 100% is not recommended because it will really try to go to the end of the earth looking for that last spot. It's inefficient. The all-important resolution value. Earlier, if you remember, we decided that our maximum resolution was 1.5 angstroms. So we'll put that in. Minimum redundancy, 3. For a high resolution data set, you might want more, so 6. In the rare case you want to collect anomalous data, to do copper SAD phasing, you can click this. For width per frame, that's usually set at 0.25 degrees. There are special cases where you want to change that. Finally, your exposure time, we determined that earlier, that 30 seconds would be the best. And we decided the distance would be 50. Now, it always has a suggested distance listed here. You pretty much want to ignore that. Even the representative from Rigaku said that that's not really a good idea what this suggests. You're better off determining it empirically, which we did at 50 millimeters. Okay, so there we have our resolution we're trying to get, distance that we know we won't have overlaps, and exposure time. Now if we go over to the Advanced tab, I always like to click this, where we get one scan with 2 theta equals 0. What that's going to do is it's going to force that first data collection sweep to have 2 theta 0. That's going to make it much easier to index your final data set and integrate it. Without that, it may start at a high angle, 2 theta, and the indexing might be difficult. Also, I like to limit chi to maybe 30 degrees. In certain cases, it's okay to go higher than that, but you will have to test those high chi angle collections before you just shoot some individual frames, because it is possible that at a high chi angle, particular pins, you'll actually get the copper portion of the pin in the beam, which is not good. Okay, and in case you're worried, there's a collision avoidance file that understands the geometry of the way the goniometer is set up, so it won't crash the detector into itself or into the omega table or anything. Okay, so at that point, we'll generate a new strategy, and it'll think about how to collect what you asked for. Okay, so we'll give you a little happy face here and let you know that it was able to come up with a collection strategy. So the first scan is at 2 theta that we requested it to do that, and it's only going to do 10 degrees, so 40 frames there. And it's going to do 5 scans. So after 5 scans, it should be 99% complete. And you can see in these graphs down here, scan 1 is at 2 theta equals 0. Scan 2 is collecting quite a bit of the completeness. Has a redundancy up to 3 by then. And by the end of scan 5, it's done what you said. This graph here is important, where it identifies overlaps. So it's tempting to put the detector up closer, so we'll have less scans, and the experiment will go quicker. So if we were to move the detector all the way up, also what I didn't mention is that it optimizes the chi and phi angles for each scan to collect all of your HKL spots as efficiently as possible. So here at the close distance of 27 millimeters, it says we can do everything in 854 images, 3 scans, so it'll be much quicker. But if we look at our overlaps and percent overlaps, that's quite a few. So that's going to be kind of a poor data set at that point. So let's go back to what we had of we'll try 60 millimeters. If you remember from our initial images, 50 looked good, 60 also looked good. So 60, since the detector's farther away, it's going to want to move 2 theta over farther and likely collect more images. So it's going to collect 1837 images at 30 seconds apiece. It says it'll finish at 9 o'clock tonight, so that's an 8-hour data collection. That's not too bad. For a redundancy of 6, resolution of 1.5 in-house. So once we've agreed upon a data collection strategy, we'll use this button here, export scans to HKL 3000R, and exit. If you remember, I said earlier, in this particular experiment, it's a molecular replacement experiment. So before I collect this high resolution data set, I want to collect a quick one, solve it just to see if my ligand that I soaked in is actually in the active site. So at that point, I'm going to go back to 2 angstroms, minimum redundancy of 3, exposure time, 0.5 seconds, yeah, the Rigaku strategy doesn't allow you to go below 1 second, but we can change that later. And we thought the distance at 40 millimeters was still good. There was a little bit of overlap going on, but like I say, for a quick data set just to do molecular replacement, this will work. So let's generate a new strategy. Okay, so in this case, it's going to do a single scan at 40 millimeters, 362 images. So that'll be done at 1:30. It's 12:47 now. Okay, so once it's calculated a strategy, we can see here that it's going to collect 362 images. If we're doing 1.5 seconds per image, that's going to be 180 seconds. So the actual exposure time is going to be about 3 minutes of x-rays. Here we go to export scans to HKL 3000 and exit. It's going to confirm that you want to exit here. And then if we look back at the HKL 3000 package, we'll have what the strategy will get imported here. At that point is this setup DC button here. That's the critical one to get it to collect what you want. So when you hit that, it's going to pop you over to the collect tab in the multi here, the multi collection interface. And what you want to do is simply confirm what it's doing. So it's collecting 362 images from minus 36 omega until 50 plus 54.5 omega, distance 40, time per frame is 10 seconds. We actually wanted 0.5. There is a little bit of a bug there where it doesn't always bring the time per frame correctly from the Rigaku strategy into the collect tab. So you always want to check that. Of course, you always want to check all your values. So we're ready to go. We're going to collect that now. There's our data set. Okay, so now it's collecting the 0.5 second frames. So we'll let that finish, and then when it finishes, we'll go back and set up that high resolution data set. Okay, so our low resolution data set at 0.5 seconds per frame was done in about 3.5 minutes. So I integrated it, scaled it, solved it with molecular replacement, and hey, our ligand was in the active site. So now I want to go back and collect a higher resolution data set. It's only been 15 minutes, so the crystal is still on the goniometer and ready to go. I reloaded up our strategy for the high resolution, where we're going to have 1.5 angstroms, redundancy of 6. So he wants to collect 1586 images, and that will be done about 7 hours tonight. So again, we get down to the bottom here. You want to export scans to HKL 3000. At this point, it's going to exit the program. That program is the collection strategy program. And it will load them up here. And then you want to set up DC for data collection. It'll jump back to the collect tab, and it's got all 5 scans lined up here. So you want to go through and make sure these make sense. The first, again, the time per frame seems to default to 10 seconds. So we decided it was 30. Okay, our oscillation width is correct. Our distance is constant. Our time per frame is constant. The chi and phi values adjust to optimize our data collection, and the 2 theta spends most of its time over at 23 degrees, and that's to get our reflections out to 1.5 angstroms. The estimated time says it's 11 hours. It's actually going to be a little less than that. There's the way it calculates it, it doesn't take into account the fact that the pixel array detector is shutterless, so it overestimates the time. Okay, once you're confident with this, we'll hit collect sets, and the collection is going to be very similar to that initial data set, except it's going to take longer and give us more data. So that's basically the conclusion of how to use the Rigaku strategy within HKL 3000 to collect high-resolution data sets at home, as well as low-resolution data sets to really determine how your crystal is.